Okay, my name is Hyunchul Park, and I'm from SUNY Newport. Today, I'm going to talk about spectral heat content for alpha stable processes in C11 open set. This talk is based on a joint work with Reming Song, and the paper is submitted and is available in archive. So my plan is I'm going to introduce the main question and state the main result, and I'm going to explain the sketch of the proof. Okay, so let's start with the spectral heat content. Spectral heat content measures a total heat when there is a heat on a domain D, and there's an initial temperature is a 1, and there is a Dirichlet boundary condition so that heat decays as time goes. And then spectral heat content is the total heat after a certain time t. At time t, there is some heat and it decays, and we want to measure the total heat. So physically, this is a very natural object to study. And this can be written as integral of the solution of heat equation, where this Vd is a solution of this heat equation with the initial condition and Dirichlet boundary condition. And this Vd can be written in terms of probability terms. And this Vd can be written as a probability that the Brownian motion starting from position x survives until time t. So there's some relationship between this heat equation and probability and spectral heat content. So in this talk, we are going to study spectral heat content for stable processes. So what is a stable process? A stable process is a Levy process whose characteristic function is given by this form, where this alpha is called a stability index and is between 0 and 2, including 2. When alpha is 2, it is Brownian motion. And when alpha is strictly between 0 and 2, this is a pure jump process. And stable process has a very nice property that it is self-similar. That space variable and time variable has some close relationship. So they have this relationship where this equal is equal in distribution. So this is a main object we want to study. We want to study spectral heat content for stable processes. So the definition is exactly the same as a spectral heat content for Brownian motions, except that the Laplace operator, which is an infinitesimal generator of Brownian motion, is replaced by infinitesimal generator of stable processes, which is a fractional Laplacian. So we define spectral heat content Qd alpha t as in this way, where this tau d alpha is a exit time of a stable process. So everything stays exactly the same, but Brownian motion is replaced by stable processes. And we are interested in the asymptotic behavior of the spectral heat content and its relationship to underlying D. So that's one reason why people are interested in spectral heat content, because for Brownian motion case, spectral heat content has a asymptotic expansion near time 0, and it has some information about the geometry of the domain, such as Lebesgue measure, perimeter, and mean curvature. So let's talk about spectral heat content for stable process. So dimension 1 case is known by result from Aquino Valverde in 2016. And so spectral heat content has 3 different heat decay rates depending on stability index alpha. Between alpha, when alpha is 1 to 2, then the rate is t to the 1 of alpha. Alpha is 1, there's an extra log 1 over t term. When alpha is between 0 and 1, the rate is t instead of t to the 1 of alpha. And then the second term is given by this expression. So this is a dimension 1 case for this open set. And we are interested in high dimension because we know dimension 1. For high dimension, when alpha is between 0 and 1, Then stable process is a bounded variation. The sample path is a bounded variation, so that it can be covered by this result. So when alpha is between 0 and 1, this is a second term of spectral heat content for stable processes for arbitrary dimensions. So we know dimension 1, and we know when alpha is between 0 and 1. So that the remaining case, we are interested in the remaining case, which is a high dimension. D is bigger or equal to 2, and alpha is between 1 and 2, including 1. So this is the main question. We are interested in spectral heat content for stable process for remaining case, which is a high dimension, and alpha is between 1 and 2. And this is the main result. So let D be a bounded C11 open set. So C11 open set means it is the boundary of this domain is a C1 function whose gradient is a Lipschitz. So geometrically, it has some nice property that it has interior and exterior ball conditions. We can put two balls in every boundary point of D. And the spectral heat contents has this asymptotic expansion. And this expression is exactly same as spectral heat content for stable processes for one dimension case when we interpret this perimeter of the domain as a 2 when D is an open interval. So the result is exactly the same form, but the proof for dimension 1 and the high dimensions are very different. So let me explain the idea of proof. So there are two cases. First case is alpha is between 1 and 2, and second case is alpha is 1. So alpha is between 1 and 2, then proof is easier. And the main idea is a scaling property of stable processes and half space approximation. So if we use these two properties and do some computation, then we could prove that this result. And so I'll move on. So next case is alpha equal to 1, and this is more difficult. So there are two parts. We want to find the second term of spectral heat content for alpha equal to 1, or Cauchy process. So the low bound for heat loss is we are going to compare the spectral heat content with the regular heat content. So this is similar to spectral heat content, but there is no Dirichlet boundary condition, so that heat can move back and forth freely. So heat loss is actually less than the spectral heat content. So HDT is a regular heat content. So this is the upper bound of QD. Or if you flip reverse the sign this is a heat loss, and heat loss of a spectral heat content is bounded above by heat loss of a regular heat content, and we know the limit of this guy in this form by previous result. So this gives a low bound for the spectral heat content. So let's talk about the upper bound. So upper bound, we are going to compare the spectral heat content for stable processes with spectral heat content for subordinate killed Brownian motions. So stable process can be realized as subordinate Brownian motions or time-changed Brownian motion, where time change is stable subordinators. So this spectral heat content is a spectral heat content for killed subordinate Brownian motion, time-changed Brownian motion, and killing later. And we can reverse the order of killing and the time change. So we think about the killed Brownian motion. We observe the Brownian motion until it exits the domain. And for that killed Brownian motion, we make the time change. So that's called a subordinate killed Brownian motion, killing first and the time change later. And because this is observed from the killed Brownian motion, it is less than QDT, or it has this relationship. So we have a upper bound for the spectral heat loss. And using this idea of subordinate killed Brownian motions, we can prove that this expression, and we want to prove this term converges to 0. The gamma function, this is a big O alpha minus 1. But this is a delicate part, and this integrand is a both of this order, so that this integral is a asymptotically equal to 1 over alpha minus 1. So that they don't cancel out each other nicely. We want to prove that this term converges to 0, but they are the same order, but these two are exactly the same main term. So that when we subtract these two terms, they cancels out. The main term cancels out, so that main term vanishes. And so that we could prove that this term, this auxiliary term, converges to 0 as alpha approaches 1. So that this guy is a upper bound. So we used an exact cancellation argument. So the proof is a little bit delicate in this case. So that's all. And here are some references. And the main paper is this last paper. And that's all for my presentation. Thank you for listening.